1876, a paper called On the Extra Current was published in the Philosophical magazine. Its author was an unknown 26-year-old called Oliver Heaviside. This was a man with no formal scientific or mathematical training. Yet, out of nowhere, Heaviside had pieced together something remarkable. He had derived for the first time the Telegrapher equation. What it described would forever change our understanding of how signals propagate through transmission lines. In 1855, William Thomson published a theory which explained the propagation of signals through cables and helped establish the first transatlantic telegraph link. He would later be made Lord Kelvin in recognition for this work. To understand Thomson's theory, we need to go back 3 decades to Paris and Joseph Fourier. In his 1822 book, The Analytical Theory of Heat, Fourier put forward a new set of ideas that would revolutionize the way physical systems are modeled. Fourier found a mathematical connection between the way heat flows across time and through space. The basic mechanism is simple. Heat will flow from hotter regions to cooler regions at a rate which is proportionate to the difference. The process plays out over infinitesimal time spans and across infinitesimally small regions. Consider a one-dimensional rod. The time rate of change of the temperature across a small span of time depends on the difference between itself and its 2 close neighbours. In one dimension, this behaviour is encapsulated in one equation, the heat equation. What this tells us is that for any microscopic section of the rod, the time rate of change of heat is proportionate to the difference of differences with its 2 neighbouring points. This is the mathematical description of diffusion, the smoothing out of a signal over space due to disturbances in time. The incredible thing is that this microscopic behaviour can be extrapolated to the whole system, if we can find a solution which satisfies the equation for all x and all time. The solution is then essentially a simulation of how heat will evolve over time and space. But the problem is that a solution is actually quite hard to find. But what Fourier did next would catapult his work to the next level. Fourier discovered that if your initial condition follows a sinusoidal pattern, a solution which satisfies the heat equation is trivial. Over time, a sine wave simply becomes an exponentially scaled down version of itself. He had found a cheat code which allowed a simulation of physical reality with the most trivial of mathematics. But practical systems do not have initial conditions which exhibit a sinusoidal pattern. But Fourier realized that any arbitrary function could be represented as a sum of sinusoidal waves. Once you find which sine waves make up your signal, the solution to the heat equation is simply the sum of an increasingly scaled down version of each of them. In other words, Fourier had found a way to use his cheat code to simulate an arbitrary initial condition. In 1855, William Thomson proposed a model which explained the propagation of signals through electrical cables, and it would lead to the first telegraph connection between America and Great Britain. Thomson's paper had 2 major breakthroughs. First, he had modelled the cable as an infinite series of resistance and capacitance, the first distributed parameter transmission line model. From this, he discovered that the propagation of voltage and current followed the heat equation. Voltage and current diffuses into the cable in the same way that heat diffuses into a metal. His second major breakthrough was to find an expression to simulate the propagation of the signal due to an impulse at one end of the line. But the hard work had already been done by Fourier. Thomson simply repurposed Fourier's fundamental solution for the heat equation, and by doing so, he could simulate the propagation of voltage and current due to the telegrapher's momentary application of a pulse. Thomson's analysis was a triumph, but his ideas were not widely accepted at the time. And this was mainly because there are a few inconvenient characteristics of this type of propagation. And when the first transatlantic cable was laid between Ireland and Newfoundland in Canada, a problem that was to plague communication engineers for the next 150 years would present itself for the first time. Fourier's analysis of the heat equation showed clearly that higher frequencies travelled faster and attenuated faster than lower frequencies. So if our initial condition starts life as a composite broadband spectrum, the cable will diffuse apart the signal, a process we know today as dispersion. Just like in Fourier's analysis of heat, any signal injected into the line will have its frequencies torn apart. This is the nature of diffusion, the infinitesimal averaging of the signal over small increments in time and space. After a 2,000-mile journey, all that's left is the slow-moving, lower frequencies. How this played out in the 2,000-mile-long transatlantic cable was entirely predicted by Thomson. Consider that the receiver detects a pulse based on the peak of the current, and so the question arises, how long after the injection will that peak happen? Thomson showed that the delay is proportionate to the distance squared. If you double the distance, you quadruple the delay. If you want fast communication, a long cable is a disaster. Thomson also showed how this phenomena could be mitigated by simply minimizing the resistance of the cable. But this adds cost, and the company responsible for the cable did not follow Thomson's advice. On August 16th, 1858, the first transatlantic message was sent between Queen Victoria and President Buchanan. It was 98 words long and took 16.5 hours to transmit. When the cable inevitably failed, Thomson was never ignored again. What Thomson showed and what the transatlantic cable demonstrated was one aspect of the telegrapher's equations, but it was missing something. In 1873, James Clerk Maxwell published his treatise on electricity and magnetism. Maxwell had spent the last decade developing a mathematical model which claimed to connect the two phenomena. When his work was published, it did not immediately cause a sensation. Many simply did not understand its significance. But there was one man who instantly took to Maxwell. His name was Oliver Heaviside. Who was Oliver Heaviside? That question has many answers, so let me give you a few of them straight away. He was a man born in mid-Victorian times at a low social and economic level, who, with no formal education after the age of 16, eventually came to be accepted as the intellectual equal of the finest scientific minds of the day. Born into poverty in 1850, Heaviside had few privileges. But he did have one stroke of luck. He took his first job at the age of 19 as a telegrapher at the Danish Telegraph Company, a position he was recommended by his uncle, the famous telegraphical pioneer, Charles Wheatstone. He was by now well versed in the practical side of telegraphy. His time as a telegrapher would be his first and only formal job. Heaviside was never married. He was a recluse. When he returned, it seemed that he made the choice to dedicate his life to mathematics, and his first task was to understand the new work of Maxwell. In 1923, Heaviside spoke of his youth. I remember the first look at the great treatise of Maxwell when I was a young man. Up to that point, there was no comprehensive theory, just a few scraps. When I first saw on the table in the library the work that had just been published in 1873, I browsed through it and was astonished. I saw that it was great, greater and greatest, with prodigious possibilities in its power. I was determined to master the book and set to work. I was very ignorant. I had no knowledge of mathematical analysis, and thus my work was laid out. Maxwell had showed that when a charge accelerates, it creates a disturbance, which other charged particles in the region react to. For a circuit, this reaction takes the form of a voltage drop, which opposes the initial acceleration of current. Heaviside would call this phenomena inductance. But in 1876 he would show for the first time how inductance unlocked a new mode of propagation on transmission lines. In Thomson's diffusion model, it is true that the voltage drop dV by dx must always be proportionate to the current, where current is dq by dt. In 1876, Heaviside discovered a new type of phenomena, which results in another type of voltage drop, which only happens when charge accelerates. Heaviside called this inductance. It creates a voltage drop which is proportionate to the rate of change of current. This subtle difference has profound consequences. The resistive and inductive voltage drop both exist together simultaneously. The first is proportionate to current, the second to the rate of change of current. Consider that in Thomson's model, when we charge a capacitor, the rate of change of its voltage is proportionate to the rate of change of current. But the voltage drop along the line is proportionate only to the current, not its rate of change. This creates diffusion. The voltage or current projected along the line is always different to the voltage or current you inject at a point. With Heaviside's model, the voltage drop along the profile is inductive. Its rate of change is proportionate to the rate of change of current. Therefore, the change in voltage along the line is a perfect reproduction of the change of voltage across the capacitor. This is no longer diffusion. What Heaviside described was a wave. In his 1876 paper, Heaviside presented an equation which incorporated both diffusion and wave-like properties. This equation is still taught in textbooks today. Heaviside sought to find a solution to this equation, and at this point, if you did not know Fourier's work, you would have no clue why Heaviside started by solving the equation for a simple sine wave. This was, of course, Fourier's building block to piece together more complicated signals. Heaviside quickly found a solution to the special case of a harmonic sinusoidal wave for both voltage and current. He then moved quickly on to an application. His first case study was the discharge problem. Imagine a transmission line with the source on one end and ground on the other, with a constant current. Then, at time is equal to 0, ground the source and model its discharge. The voltage in this case will look like a ramp with 0 boundary conditions. Such a function has a well-known Fourier series comprising only harmonic sine waves, for which Heaviside already had the solution. This allowed Heaviside to see something nobody had seen before. This is what he called the extra current, an alternating oscillation of current. This current travelled and bounced back and forth in a way that was different to diffusion. I've written code to try to model Heaviside's mathematical analysis. You can see here exactly what Heaviside is talking about. When the source is grounded, it is essentially imposing a step response to the transmission line, a transient which moves as a wave, but waits some time and the transient returns. At this point, the source itself bounces the signal back into the line. This is the oscillating current Heaviside talks about. We can view the current also as a function of position, and here we can see the front of the transient as it travels backwards and forwards. At the age of 26, Oliver Heaviside had derived the Telegrapher's equations. His work had shown that the propagation of signals through transmission lines is dominated by two phenomena. First, diffusion, a process first understood by Fourier to explain heat flow, then by Thomson to explain the flow of electricity through a 2,000-mile long cable which would bridge two continents. Then Heaviside combined diffusion with a new phenomena, wave propagation. Both diffusion and wave propagation exist together and still provide the most comprehensive theory of signal propagation on transmission lines.